from Australia, Pavel Bedrikovetsky, and he will speak about exact solution. You see the title, exact solutions upscaling for one-dimensional hyperbolic flows in micro heterogeneous media. Okay, Pavel, you're welcome. Please begin.
So can I start, please?
Yes, you should.
Okay. So far I can see only gentlemen, but if I'm mistaken, ladies and gentlemen, good afternoon. In Australia, it is good middle of the night. And I will speak about simple hyperbolic equation from the textbook, where we enter just simple difference. We make flux f function not only of unknown, but also of the linear coordinate x. Can you see slides, gentlemen?
Yes, we see them, yes.
And can you hear me well?
Yes, everything is perfect. Please proceed.
Okay, thank you. This will be about hyperbolic equation from textbook, where is introduced flux dependency on x. Sorry, first it is here 2 a.m. and second I got difficulties to enter this website. So I forgot to thank Professor Krasilchik and all members of the seminar for inviting me and for silver memory. Thank you for this. So the basic for this formulation is as following. This is a conservation law for mass. And very often flux density times viscosity is function of density. So this function is property of fluid and of medium. Medium could be heterogeneous. So this property f of rho could be function of source of x. This is also lead to the same equation, conservation law, where flux depend on x. You can hear me okay? Hello?
Sorry, Pavel.
Yes, we see and hear you.
Yes,
Yeah,
everything,
okay.
Everything is fine. Please proceed.
Okay. Well, if you will have some comments or questions, you interrupt me without any hesitation, please. And I proceed. So the question is, first, if I model some system, which are the exact solutions? And second, is it possible to average it over x to introduce so-called effective properties? So it could happen when S is density or saturation of two-phase flow in porous media. And you can see subterranean layers and 2 points in the subterranean reservoirs over which flow occurs. And if this line intercepts different geological areas, appear of dependency of x. And also in order to study it, we take out so-called core reservoir sample, taking in laboratory and model the flow in rock which corresponds to different strata, so-called composite core. So also this flux will be function of x.
And what is alpha?
Sorry?
What is alpha in this picture? CO2, then with tube, then water, and upwards we see alpha and unit minus alpha. What is alpha?
Let us say in this complex reservoir there are two phases. Let us say white phase, one sample of rock, and another is gray sample of rock. So when over this well I do coring, so I take sample of my rock, in this cylinder I will have white highly permeable, gray low permeable, high gray, high low. It is called composite core. So it is just heterogeneous example of heterogeneous media, in this particular case periodical one. Okay? So ambitious of this project is as following. Let us say if I have got conductors in series, resistance is average arithmetics. If I got parallel conductors, the equivalent resistance is mean harmonic. So like this, we want to introduce averaged or equivalent or upscaled property of function f of s, or flux, which average over x, and averaging is in one or another sense. This is the goal of this presentation. And another challenge which could occur leading to the same formulation is as following. Let us say I have got a numerical grid, which is shown in this figure, and variation of f versus x is too dense. So vibrations over x occurs very frequently. So I don't have enough computer power to perform numerical simulation of this model. So I need to upscale it to decrease number of nodes or number of cells. So let us say I need to average every 10 cells. So to decrease number of cells, one order of magnitude. How, if I got different f of s in different cells, how to upscale it, how to make average over 10 numerical cells. And the answer I will give you straightforward. The answer is as following. If those are flux function versus different x, I calculate not f of s, but inverse function s of f. S of f. So I fix f, take inverse, and average over x. So this is exactly a recipe as in electricity they're saying about parallel or conductors in series, how to upscale this flux function. It is just take inverse and to take this average. And then you can prove that if I have, let us say, analytical solution in cells x0, x1, xn, so I got numerical solution of overall x. it coincides with solution of equation without x in these points. So if I average over each cell, solution of upscaled and real scale models coincide in node points. So this is main result of this work. Do you want maybe to discuss it, maybe ask something, make some comments?
I think that when comments or questions arise, you will hear them. So proceed until you can. Don't bother.
Okay, so let us say if I am capable to solve this problem, but I'm incapable to solve this problem with family, X families of these flux functions, I just average inverse function over variable X and go ahead with f of S. And both solutions coincide in nodes. In order to deliver you this message from left half of an hour, I will waste maybe 15 minutes reminding how to solve Riemann problem for f function of S. And again, if I repeat into details textbook, you just let me know. And I will try to make it very transparent. Then I will prove very simple fact that in the system with S and X, Riemann invariant is flux F. So I will show you that in this problem, I will call it microscale problem. In microscale problem or real problem, Riemann invariant is flux by itself. Then I will show how to solve Riemann problem in several situations, including for any initial, any continuous solution of any initial boundary value problem, show upscaling, and then show possible extensions of this approach, which presently we are working upon. Something I forgot to tell from the very beginning, I need to acknowledge two PhD students whom I am honored to supervise. And because the product of upscaling of averaging, I will call large scale problem. And when we will be talking about X-dependent flux, it is microscale problem. That's how we will call it. So Riemann problem for this equation, this is hyperbolic equation, assuming the density S, density is S, f of S is flux, and unknown variables is S as a function of X and T. We will solve here Cauchy's problem, where initially value at X negative and X positive are constant, or initial boundary value problem, when at T equals 0, we got constant, and at X equals 0, another constant. So in conservation laws for Cauchy or initial boundary problem, what is to the right of 0 is called R, what is called to the left or at X equals 0, they called L left. So this problem allows, obviously, for self-similar solution. If we assume that S is a function of two variables, x and t, can be presented as a function of such a group variable, x divided by t, we substitute it into equation by itself and got two kinds of solutions, S of v. First is constant, and second v if is derivative, f prime of s. Very simple substitution. So obviously, if f is vector function, so it is system n by n conservation laws, still S constants are solution, but V will be eigenvalues of the matrix df by ds. So because independent self-similar variable is V, x by t, its velocity. So S by V means that every value of S is transported with the given speed v. And this solution x by t or v equals f prime of s. So this is solution. Again, solution of inverse function, not s of v, but v of s. V of s, x by t, it is f prime of s. So let us say we are solving a Riemann problem, left data point L, right point R, and solution consists of constant at point L, this wave from L to R given by this equation, and constant state in point R. And this solution is continuous. So let us solve now point L as J, point R as I, curve 1, and solution is S function of V, x by t. It's constant as J when velocity change from 0 to tangent in this point. Then this wave x by t, it's prime in the over the curve 1. And when we comes to the point R, whereas R, it's petroleum nomenclature, and sorry for this, I should change it to L and R. It is again constant when velocity change from this tangent to infinity. That's continuous solution. So we can see that along this continuous solution, V x by t, who change from 0 boundary condition x equals 0 from point L, here v equals 0, x equals 0, and t equals 0 initial data corresponds to v tending to infinity. So this velocity over continuous solution changes monotonically from R to R for a convex function. So it changes from tangent in point L to point R. if we want to come to the upper point to lower point, so here minus is left point at negative x and plus as point r at positive r, v will increase. One could prove that there is no continuous solution. So we need to expand the space of admissible function and to look for solution in set of discontinuous functions. So there are a lot of discontinuous solutions, and we make such a definition that shock or discontinuous solution is admissible if it is limit of continuous solution of this equation with vanishing viscosities. And it is possible to prove that discontinuous solution for hyperbolic equation, whatever Cauchy problem for hyperbolic equation, exists and is unique if and only if first mass balance occurs on the shock. So jump in flux equals jump in variable in density times velocity of the shock, so-called Hugoniot-Rankine condition. Then stability condition in linearized formulation, which was, it is Lux condition, perturbation in linearized system. And it is this condition that velocity of the shock d should be lower than velocity of characteristic from behind and higher than velocity of characteristic on top. And if we discuss more general formulation of stability, stability with respect to any perturbations, it's a Olenek condition. It is that segment minus plus should not intercept, should not cross fractional flow curve f of s. So these three conditions, it also was proven by Olenek, provides uniqueness and existence of solution for whatever flux function, whatever Cauchy problem. Three conditions. So for this continuous solution, so for this discontinuous solution, excuse me. So for this discontinuous solution, jump from Sj to Si, you can see that segment linking two points behind front and ahead of front doesn't cross fractional flow curve. And this tangent is less than velocity of characteristic in point behind and above point of characteristic above. So we have got now two types of continuous solutions, as I told before. It is constant states, and those given by the formula that velocity v equals f prime of s, and shock waves, jumps from one state to another state. So if we are talking about whatever form of fractional flow, so solution of Cauchy or initial boundary value problem from L to R, if SL is higher than SR, is jump to the tangent point, then wave and another jump. And if L is lower than R, it corresponds to wave, one jump, and one rarefaction. So actually, if point L value of unknown is higher than in point R, it corresponds to upper envelope of fractional flow curve. And if we are talking about case of L to the left from point R, it is lower envelope. So this is a theory of Riemann solution for property of Riemann solution for hyperbolic conservation law. If there is no questions, I will move further. So if for this equation I know f of s, I can solve this problem by self-similar solution for constant Cauchy values. Now let us discuss inverse problem. Let us assume from laboratory, I run in laboratory this physics system, and I put a rate meter at point x equals 1. So I know in this point f flux. The question is how from flux f of t at the outlet of my sample calculate f of s. In order to do it, I select triangle, which corresponds to whatever point t, and integrate over this triangle original equation. Of course, it is 0. By Green's formula, it equals to integral of differential form of mass, f dt minus s dx, over this contour, over this triangle. What is nice about it, that one side corresponds to initial data, another side corresponds to measured data, and hypotenuse corresponds to x divided by t equals 0, or v equals 0. And solution is self-similar. So integral 1 from initial data, it's constant. Integral over second side 2, it is integral of known data. And in right hand side, I got integral from point 0, 0 to point 1 t, over which s and f are constant. So this is formula which is linking s, saturation over this curve, with known measured data. So again, I don't plot here f of s, I plot s of f, and for given f, I calculate this product, calculate integral, and I have got s. Very important note is that this inverse solution does not involve direct solution. I just need to know that it is self-similar. This is important Weld's method, which is used in a lot of applied scientific areas where this equation is valid. Is it okay? Do you want to comment?
No, please proceed.
So now this is our equation. I multiply by derivative, df by ds, and in first product, I can put f below the partial derivative. So df by dt, it is df by ds times ds by dt. So this form of equation immediately suggests that along characteristics with the tangent f prime, df by dt equals 0. So f flux conserves along characteristics. And this is very simple fact which will give rise to all other speculations. Osia, how long I have got more?
Well, just a moment. Well, approximately until 9 o'clock Moscow time. So you have
So,
a little bit more than 1 hour.
so how many minutes I have got more to proceed?
I told you, if you want to measure it in minutes, then you have 64 minutes.
Okay. I believe I will finish, if I will finish in half of an hour.
It's
then
perfect.
will-
Yeah, well, don't be in a hurry and just try to be clear.
Okay, very good, very good. So, thank you, Osa. In characteristic form, along these characteristic lines, dx by dt equal f prime, f conserves along characteristic. So along each characteristic, if I take inverse function with respect to s for given f, s is a function of x. I will call, and now this allows me immediately to determine implicit expression for each characteristic carrying this value f. So if I fixed f along this characteristic, s is a function of x. So right-hand side function of x. And I can solve it by separating variables. So it is not x of t, but it's t of x, inverse function, which I will call t, it is tau of xf. So explicit formula for characteristic. And now, based on it, I can solve one by one several problems, several Cauchy problems. So let my f of s vary from curve 2 to curve 1. So curve 1 corresponds to x equals 0. Curve 1 corresponds to x equals 1. So near to x, 0 in the origin, occurs this solution which we described before, so-called wave, where velocity v changes continuously from point 0 to point 1. It monotonically increases. So velocity, which is tangent of this curve x by t, change from tangent in point 0. This is upper bold curve. Then moving along this curve, when f increases continuously, velocity increases, which is values of f2, f3, and when it reaches value f equals 1, tangent grow up to the tangent point in point 1. So it is wave. Along each for each value f, for example f2, I plot here F2. F2 is constant. And I can see here how from curve 2 to curve 1, tangent rises. So for larger f over x, when I move from curve 2 to curve 1, for constant f, tangent rises. So you can see that at higher values of f, velocity of characteristic increases. But if I take lower value of f, f3, velocity of characteristic declines. So velocity of characteristic declines. For f equals 0, we can clearly see that tangent should decrease. So characteristic is given by convex curve. In point 1, velocity of characteristic increases. Velocity of characteristic increases, so it is a concave curve. And if I fixed moment t1, so there is zone s equals 0, you can see this plot, and then mixture, in the mixture zone, s continuously increases from 0 to 1, and ahead of this mixture zone, it is 1. And at later moment t2, there is continuous value until characteristic f equals 0, s equals 0, and then this piece arises. So you can see how this profile of solution propagates with time inside limited interval of x from 0 to 1. So small times, it is continuous state wave, another continuous state. And when part of this wave already exited this interval, only piece remains inside the interval. So it's continuous solution for convex fractional flow curve. Now, this is numerical simulation when fractional flow varies from x equals 0 to x equals 1. So the solution from 0 to 1, as we discussed, for independent x is shock, and it remains shock. So just for fun, there is extremely high resolution numerical scheme called Champagne code, and you can see that for a variation of fractional flow curve with x, it gives you exact shock. So you can see that solution is independent on intermediate values of flux function. So continuous solution, when flux functions are convex, it's continuous. When it is concave, it's shock. Let us now discuss a mixed problem when initially fractional flow at x equals 0, it is curve 5. At some intermediate, so curve initially it was concave, then it becomes convex with x. So curve 5 corresponds to x equals 0, then it becomes less and less curvilinear, and in intermediate points xc, it became straight line. And further, it is convex. So at x equals 0 occur shock, as we saw for whatever form of concave curve, it remains shock. So it moves over the x with constant velocity. At point xc occur configuration where this f prime of s velocity, it is constant in curve 3, and then it became more varying in high and high intervals for curve 2 and curve 1. So you can see that for small f, velocity from 3 to 2 to 1 decreases. So this is trajectory carrying value f equals 0. And for large f, from curve 3 to curve 1 through curve 2, velocity increases. So you can see curve carrying value f equals 1, and intermediate characteristic line carrying all intermediate values of f from 0 to 1. So again, at moment t1, Americans are calling it profiles. So I cut at the moment t1, and I see how my unknown varies. It is 0 until shock, and 1 ahead of shock. At the moment t2, short after appearance of this wave configuration, S varies f equals 0 behind the mixture front. Then in mixture front, it varies from 0 to 1 continuously, and ahead of the mixture zone, it remains 1. At the moment T3, where part of mixture zone has already exited my specimen or my media, where x varies from 0 to 1, it varies from, it continuously increases from 0 to some intermediate zone. At moment 4, it is just zone 0. All mixture got out. My fluid which I inject fills overall media. So we call it solution transition from shock to continuous wave. We start at the very beginning of media with shock, and then it transforms to continuous wave. I was lazy to write down solution in these 3 zones. Now vice versa, transition from continuous wave to shock. So x equals 0, it is concave curve. X equals 1 is curve 5. So we start at concave curve 1, then second derivative decreases, curve 2. At point xc, second derivative equals 0, so it's straight line. And at curves 4 and 5, second derivative is negative, so it is concave curves. So at x equals 0, appear wave, self-similar wave, where f varies from 0 to 1. So here characteristics, they vary from continuous characteristics, they vary from tangent in point 0. You can see it as very large one, curve 5, to very small one, curve 1. So you can see here this cone of characteristic lines, and you can see that along curve f equals 0, f velocity decreases. Over f equals 1, you can see here that velocity increases. And f prime of s, when x tends to xc, tend to constant. So all tangents from x equals 0 to s equals 1. So velocity for s equals 0, they decrease up to this constant, and f large f they increase up to constant. So at point xc, all these characteristic lines are parallel, and then you can see that velocity at low f, they start increasing. They start increasing, moving from curve 3 to curve 5. And for large f, f equals 1, for example, f equals 1, moving from 3 to 5, velocity decreases. So at some point, they will intersect. So they appear such a shock. So after the moment when characteristics above this time, above such a inflection point, their velocity increases and below decreases, will appear shock. This shock will propagate with velocity, which can increase or decrease depending on geometry of these curves. And at the moment it appears at the point xc, so at point xc f minus equals f plus, but then this difference between f minus and plus increases. And in the point of interception of shock wave, first with characteristic carrying f equals 0, and then with characteristic x equals 1, it will be full shock from 0 to 1. So when there will be curve 5, it will be full shock. So you can see here transition from continuous wave from 0 to xc to shock wave, which appears in point x equal xc. And then this shock value jump from minus to plus increases, reaching final value when characteristic becomes f5, corresponding to curve 5. So short moment before appearance of the shock T1, profile is zone s equals 0, then continuous zone from 0 to 1, and then S remains constant, S equals 1. Then moment after appearance of the shock T2, S equals 0 before mixture, then continuous variation until shock, then shock, and then continue, then yeah, there is a mistake here, I'm sorry. Then at the moment T1, no, it's okay, it's T2, it's jump to this, is jump to intermediate variable value, and then it must be continuous here. Yeah, very good that we already sent it to journal. Okay, so it's a pity. So it will vary until this moment, and then it will become constant. And at the moment T1, it will be full shock from 0 to 1. So also we can write down continuous solution in different areas, in different zones. Unfortunately, again, I'm sorry. I forgot here to put such mathematical calculation. So how to obtain solution in continuous zones, I already showed you. So for whatever variable f, varying from 0 to 1, for whatever constant f, line of constantness of this f is given by this equation. When we are talking about shock wave, I need to write ordinary differential equation. Velocity of shock dx by dt, it is a ratio between jump of flux divided by the jump of density. F minus F plus divided by S minus S plus. And it is ordinary differential equation. So how propagates line F equals F of S minus, we know, I showed you equation. How to propagate line with this value I also know. And these two characteristics, they arrive to front. So there will be ordinary differential equation. There is such a very beautiful, simple calculation. If I want to obtain first integral of this ordinary differential equation, for example, in this point, xf of t, I fix characteristic which arrives f minus, characteristic which arrives f plus, and integrate this equation over this area between two characteristics. So this integral equals 0. I calculate it over f equals constant and f equals f minus, f equals f plus. And this integral, this expression gives me first integral for front velocity. This I forgot to tell you. So from the fact that f is constant along characteristics, we obtain continuous parts of solution, and integrating over area bounding arrival and departing characteristics, we obtain first integral for trajectory of shock front. So also there is explicit formula for this solution. There are a lot of other configurations for different shapes of fractional flow. Very often f of s has S form. So for all two-phase fluxes in two-phase flow, f of s is S-shaped. Also, there is very funny application, but extremely widely encountered in life. It is street traffic. If S is density of cars along the street, F of S, it is flux of the cars, how many cars passes point X at unit of time. So there also often F of S is S form. So what we need to do here is this following. Let us say if F is independent on X, so F of S is any of these curves. So the solution from point 1 to point 0 of this Riemann problem consists of rarefaction and then shock. So in this case, we need to make, a line of tangent points 2, 3, 4 at x equals 0 upper curve, at x equals 0, I should put here x equals 0. I'm sorry, I put here constant xw where w corresponds to well. It is petroleum well radius. So in reality, it's x equals 0 here. You can have here this self-similar configuration, wave from 1 to 2, then jump to 0, wave from 1 to some point 2, and then jump to 0. And it's possible to show that velocity of shock is higher than velocity for whatever incoming characteristic, as Lux condition dictates us. So velocity of shock is higher than velocity of whatever characteristic in point 0 for whatever x. So these characteristics arrive to the shock. So we are saying that this shock propagates over continuous wave or along continuous wave, and also trajectory of this front first integral can be found integrating mass balance equation over area bounded by shock and by incoming characteristics. So along this area, integral equals 0, and taking integral contour integral, we got first integral for shock xf. So also solution. Now we continue with exact solution for whatever initial boundary value. So now let us have initial data t equals 0, whatever function of x equals 0, whatever value f0 of t. So such initial boundary value problem which has continuous solution. So all characteristic lines carry all values varying from S0 of x at x tending to infinity until f0 when time tends to infinity. So over boundary, when I move from x infinity to 0 and from 0 to t, S varies continuously, solution is continuous, and this is exactly explicit formula for solution. So let us here x0, we take whatever point x0 between 0 and 1, it corresponds to some f value at initial conditions, and along characteristic line this f equals constant, so my saturation is inverse function with respect to s. So it is inverse function carrying this f of s0 of x0, its started point x0, and it is this formula for this characteristic. And we take whatever point, and this upper line corresponds to a domain where characteristics start at t equals 0, and the same for boundary condition, we take whatever moment t0 and put these lines. Now the last value, the last is upscaling. So I have got solution f, solution for f of x of sx. Now I will prove that there does exist such averaged f of s that for both problems with the same initial boundary value, f coincides at x equals 1. So physically speaking, I got heterogeneous media from 0 to 1, and I'm saying there does exist homogeneous or homogenized system where f is independent on x. We consider whatever characteristic, and it is very physical, physical, real characteristic, because I don't know what is inside. I'm only interested in what is going out. So let us see, let us assume that in homogenized and microscale system, flux at the outlet is the same. So now I discuss curvilinear triangle 0, 1, 1 over t. Again, I integrate this mass balance equation over 0 over line 1 constant, over line 2 is integral of the outlet. So integral, so I know integral over this curvilinear characteristic. So let us honestly calculate this integral. First integral is constant. Second integral, it is integral of produced flux or amount of mass of produced fluid. And over this characteristic, f equals constant. It is f equals t. And over this characteristic S is inverse function for this given f over x. And it is integral from 0 to 1. So in this formula, if I average this S over characteristic or integral from 0 to 1 of this characteristic of inverse function, it is exactly value of my averaged or homogenized system. It is very important. It is very simple formula. It took us maybe a month since we understood what happening there and which phenomena is behind it, that I just take liberty to repeat it. So we consider microscale system f of sx with given flux x equals 1. Let us construct the homogenized system f of s, only f of s, where inlet data flux at x equals 0, x equals 1 is the same for micro and macro scale systems. So integral over triangle consisting of initial data where outlet or measured data and characteristic carrying constant intermediate value of f equals 0. By Green's theorem, integral over first order differential form or of mass over this triangle is 0. So for both systems, homogenized and microscale, initial data are the same, so integral 1 is the same. Integral from time 0 to time t over exit is also the same because f equals because f is the same, and this is just integral over curvilinear characteristic of where f is constant and f's are also the same in homogenized and heterogeneous system. And for a homogenized system, upscaled solution is self-similar, so it is straight line. Over this straight line, f is constant and s is constant. So s for homogenized system equals integral, it is this piece of integral s dx, integral f minus 1 carrying fx. And it corresponds to exactly this procedure. So I got f of x, and now I need now to upscale or homogenize this system. So for each f, I make s function of x, and I average it from 0 to 1. Take integral, take arithmetic mean. That's it. This is all what I was after saying today. Now let us discuss simpler cases. So you can prove that for whatever continuous initial boundary condition, whatever a problem, initial boundary value problem with continuous solution, And here you can see absolutely the same integral. So for whatever continuous solution with any initial and boundary conditions, for f of sx, answer for upscaling is the same. I can reformulate my physics problem. It's not that I put flow meter at the outlet of my core. I take X-ray or computational tomography profile S of X at some one moment, like a momentum photograph. So I want now to upscaling using such criteria that at given time, at fixed time, such S profile S of X are the same for homogenized and for microscale system. So the formula is absolutely the same. So I need to average S over characteristic line. So the system shows you that for microscale, S average is integral over this characteristic line. And for homogenized system where f is independent of x, where all characteristics are straight lines, this straight line characteristic for a homogenized macroscale system, it is just straight line linking point initial and exit. That's it. Now just some toy. At the very beginning, Osia asked, what does it mean if it is my core, which I construct, or my plug, construct of gray core, white, great, white, great, white. So obviously one curve with density alpha, another curve with density 1 minus alpha. So average for whatever f, which crosses in these 2 points, it is alpha with S1 plus 1 minus alpha S2. So I just take intermediate curve, but averaging is not over f, it is averaging over S. So there is this red is solution in point T1 for one configuration, white, gray, and it is blue curves. And red curves, it is gray, white, white. It's blue curve. And average curves or upscaled solution coincide for both solutions. So you can, for both configurations. So you can see that average curve is independent on who is first, who is second. So it is also possible, and you can see another moment also.
Public,
Yes.
These curves, they were obtained by numerical methods or analytically?
No, all analytically. All analytical method. And,
okay. Thank you.
Yes, and all analytical method. And of course, we are doing it now for another journal. We took not 6 sections, but 10 sections. And we calculated exact solution on microscale and compared it with high resolution Champagne numerical code, and it is very good agreement, very it is conservative numerical scheme, and which shocks are very well distinguished. They use Godunov's method of conserving shock, and very good coincidence. And this is averaged curve.
Okay, thank you.
Yeah, pleasure. Now, we can prove it like a theorem that if we have got interval from 0 to 1, which is separated by different intervals, in each interval, and in each interval f of s is constant. So in each interval f function of s, I can solve it by method of characteristics, and I can have solution. Then I use upscaled solution using this rule because our criteria for upscaling is the same exit number, the same exit values. Values of large scale and low scale at boundaries coincide. So it is such a simple lemma. There is another lemma. Let us assume that in each of these intervals, f of x varies. And I apply this averaging procedure in each cell. So I got low scale when f varies inside each cell, and upscaled when f is independent on x in each cell. So we can prove that at node points, f for large and low scale coincide. Now, this is not ideal, of course, because obviously the result of upscaling depends on length of domain. So if I want to upscale from 0 to 2, result will be different. Now, this solves very important technical problem besides everything else, that it gives very clear recipe how to scale up microheterogeneous system given by this transport equation. So of course, greediness moves you to expand it to overall to another problems. This solution is based on two facts. Fact number one, on micro scale, we got explicit exact solution. On macro scale, we got explicit solution for inverse problem. So when I know f of sx, I generate f at x equals 1. For whatever f of s, if I know this generated exit, I formulate f of s. So if from your life experience you have got any problem, it could be system of equations, it could be whatever, which allows you to solve inverse problem explicitly for homogenized system and for heterogeneous system direct problem, this method work. So you can call it homogenization by inverse solution. So if God bless, I will have next PhD student with math background, of course we will try to do with him some simple linear partial differential equation when exact solution is given by Green's function and inverse problem is linear integral equation. We will try to do it. Now, let us formulate some other problems which can be easily solved using the same method. Number one, our flux depends not on x but on time. Let us say a flow in very strong external field, for example, with changing temperature. Second, flux equals to density, but actually density is function of flux. It is space-dependent adsorption, the same method. Time-dependent adsorption in strong external field, the same. Now, I started saying that first equation is equation of mass balance. Let us assume that in this flow, there is one admixture, let us say salinity, which changes flux. So in this medium, this component, when I write equation for this component, density is concentration times general density plus adsorption. So as before, S and C could be vectors. So F is vector function and A of C is also a vector function. So this is system n plus 1 times n plus 1. So in this system, there is such a remarkable fact. If instead of time, I introduce the same mass coordinate as V without mentioning what we're using before, Lagrangian coordinate. And if I will write system of equations in coordinate x phi, system for C will separate from first equation. So this is there is enormous number of applications for this system. Now, for this system, so we show now, so there is in theory of adsorption, there is such a theorem. If I solve this one-dimensional system of flow with adsorption, and if Hessian matrix is negatively determined, or if A of C is concave function, solution is only shock. So if solutions of this separate system consist only of shocks, all these techniques can be repeated for this system of equations. And now I will just resume and finish up, and don't bore you anymore. So for whatever initial boundary value problem, for microscale system with x-dependent F, the flux is Riemann invariant. The characteristics allow for first integral yielding explicit formula for all characteristics. Because of Lax condition of arrival of two characteristics to each front, we can write first integral for both characteristics arriving to this front. And if we integrate this form of domain bounded by these two characteristics, the final expression gives us first integral for shock front. So this is all about exact solution. So upscaling, if we got f of sx, we take inverse function with respect to s and take integral from 0 to 1 s dx of this function. And it gives us upscaled, homogenized or equivalent homogeneous system. Now, if for explicit finite difference method, we homogenize in whatever interval delta xi from x0 to x1, x1 to x2, etc. That we can homogenize inside an interval, and solution of microscale and macroscale systems, they will coincide in points of nodes. That's it. Now you can ask me whatever questions. You can ask me even in Russian, despite it is very difficult language to learn. In Russian, I'm almost fluent. So welcome.
Okay, thank you very much. Indeed, I have questions, remarks. No one wants to ask a question or to comment the talk?
Well,
just a comment.
Please name yourself.
Just a comment. My sound is at maximum, and I can hear you very low. So I can hear, but very difficult to make it clear.
Oh, yes, it's a problem. Well, so no question, no.
Well, I have one question, if possible. Vladimir Nazaikinsky. Okay. So, is this recipe for homogenization a theorem or a practical observation?
You mean history, how this result was obtained? So historically, I don't know. It's difficult to tell. I don't know. What is very funny is that I cannot give physics meaning of this fact. So we waste now a lot of time. We spend a lot of time now in discussions in our seminar trying to physically interpret this fact that along characteristic lines f is constant. Now, very funny thing is that nobody writes in textbooks. So when we got equation when f is independent on x, Riemann invariant is S, so along characteristic S conserves. But f of S also conserves. F of S automatically conserves if S conserves. But if we introduce X, F only conserves. Now, when you look at textbooks on physics, and f prime of s is velocity over which density is constant. They're saying f prime of s is velocity of propagation of small perturbations. So what the hell, why S should be conserved along these characteristics? So there is very famous professor in Denmark, my former PhD from Moscow Times, Shapira. He is professor in Denmark University. And when we pose this puzzle for him, he proposed for two-phase flow in porous media very artificial explanation, but very artificial. I can explain it, but it will take a lot of time. It's definitely not clear. So if someone would ask such a question, we take hyperbolic equation, this, and values of s propagate over velocities f prime of s. How to explain it? What is physics meaning of df by ds, which carries what velocity is for what velocity, flux over density? So we don't know the answer, even for this simple case. Therefore, we cannot find physics meaning for this, for conservation of f over these characteristics. Volodya, did I answer your question or not?
Well, partly only. The first part of my question was, is this a theorem? I mean, could you state this assertion about homogenization as a theorem with some conditions, etc.?
Yes, of course. Only what we require is continuous f of s and piecewise existence of piecewise derivative over whatever intervals. So when people are talking about first order of this equation, in textbooks, the assumptions are the same, that f of s is continuous and it can have discontinued first derivative over discrete number of values of s. That's it. Here is absolutely the same, and you prove it straightforward.
So the answer is positive.
Yeah, thank you so much.
Yeah, okay, yeah. Thank you.
Volodya, just an observation. It is first time when we speak English, right? It's first time when we speak English to each other, right?
You mean to each other, yeah.
Yes, yes.
Okay, my congratulations. More questions? Remarks, questions? Pavlik, I have a small question. Did you compare your results with some experimental data?
With what data?
Experimental.
No, not yet. We are doing it. So I will tell you what we are doing now, and we're in the middle. So when petroleum companies are sending you real reservoir cores, these cores are short. So length is small. So when we dimensionalize equation with vanishing viscosity, this epsilon got L in denominator. So when core is short, we cannot ignore right hand side. So here will be there will be no zero, and we cannot use hyperbolic technique. But hyperbolic technique is necessary in order to make this inverse problem well posed. So what we do, and here we can see in laboratory experiments how really regularized until posed inverse problem work. So we do for them composite core, we put them in line. And then we inject simultaneously gas and water. And we measure saturation by CT, by computational tomography, and numerically we will have average profile. And we would like to see that they coincide. But what I told you, it is all proven, it is simple theorems. So mathematically there is no problem. What we actually we are doing it not in order to validate our method with experiment. We are doing these tests in order to sell it well to engineers.
Yes, but to sell it well needs to match your results with some experimental data. If they do not match, then you will not sell.
Yes, it is right. It's right. You're absolutely right. My point was different. Coincidence of result in this situation of experimental and this result of this upscaling, it is mostly validation not of this method, but validation of basic equation for two-phase flow in porous media, which is very well established. So here we are very cynical. If there is no coincidence, good agreement, it means that our cores are not homogeneous on very micro scale, or some errors in measurements, because the equations were well established more than a century ago. So, yeah.
Okay, thank you. More questions, more remarks? Well, thank you very much again, and thanks to everyone for attending our session. The next Wednesday we shall listen to the talk by Oleg Morozov about Euler equation on curved Riemannian surfaces. And well, I wish you a good week and goodbye. Thanks a lot.
Дорогие мои, я вас всех очень крепко обнимаю.
Мы тебя тоже, Павлик, хорошо. Спасибо большое.
Вам
спасибо большое. Спасибо.
Ага. Все, пока. Счастливо.
Счастливо.
До свидания.